The attendance is on, guys. Okay. So I have also uploaded the last two lectures. I know it took some time, but I have uploaded the content for the last lecture as well on YouTube, but we will cover it in the class anyhow. Let's maybe wait for 1 more minute. Okay, I think we can start. Again, the content that is here, I have uploaded it on YouTube as well as on Google Drive, and you can then go through the content later as well, and then ask me questions over email as well. But I am going to go through it in the class as well at a rather higher speed. Okay, let's start. And keep your work on projects going on. I'll probably be more free from the next week onwards, so you can contact me over email whenever you want. Okay, so as we've been doing this while, the idea has been to learn some basics of UML, right? I mean, we have not really gone into details of UML. It is also because UML in itself is so complicated and so vast that you might need a complete course just on UML to know most of the things. And even after that, there is a fair chance that you will not retain much of it, because there are far too many what can I say, there are far too many uh, conventions that UML impose, and this it imposes, so that is why it becomes really difficult to remember all of it. But the idea is that at least you should be able to read UML diagrams, right? So if I give you a UML diagram, at least you should be able to figure out, okay, what kind of a diagram is it, right? I mean, is it a structural diagram, is it a behavioral diagram, what aspect of the system is this trying to talk about? So this is the major idea, that you at least have a hang of what UML is, what are the different types of diagrams. We have only discussed just a subset of diagrams, and that too within that diagrams, those diagrams too, we have only discussed the most commonly used features. But this is the idea, use the UML diagrams at least in your projects, so that will give you a better understanding, as well as, let us say, a practice of the theory that we have covered in the class. So there's like one more thing in UML that is left, and we should not leave it behind, because when you start seeing documentation of larger projects, there is a good chance that you might see something known as an allocation diagram or an allocation view. There are two terms, allocation view and allocation diagram. View is more of a an informal term. Diagram means that I'm talking about a specific UML diagram, but usually the boundaries are not really that well defined. Okay, so people take up their own liberty in building these, in creating these allocation diagrams. So anyhow, till now what we have done is that we now understand that the system has a structural aspect and it has a behavioral aspect. For the structural aspect, we have only discussed the class diagrams, that with the help of class diagrams you can show the structure of a particular system. And for behavioral things, we have seen far too many. Probably we have seen state diagrams, we have seen interaction modeling using sequence diagrams and use case diagrams and activity diagrams. So we've seen some fair bit of diagrams in order to capture the behavior of the system. And it is important too, because behavior is much more difficult to convey. Structure, comparatively, structure is easier to convey. So anyhow, so basically, there is one more structural diagram that you might see and you might use. This is especially true if your system's boundaries span across multiple machines. Okay, so it's not really a stand-alone application which runs on just one system, but let us say it has to communicate with some other machines, or it has to communicate with a server on the internet, something like this, right? So if you have a project, or if you have a system whose boundaries span across multiple machines, then you might need something known as an allocation diagram. So the idea of using an allocation diagram is to actually show that within my, how exactly is my system distributed across multiple nodes. Okay, nodes as in multiple machines. Now the term for machines is now becoming more and more wide, okay, wide meaning term. Why? Because In the older days, a machine meant a physical machine. But with the advent of cloud computing and virtual machines, it is quite possible that whatever code you are running, it is actually running on a virtual machine, which is sitting on a physical machine, or it could be running within a container. There are cases where containers like Docker, they run over virtual machines, and virtual machines run over actual machines, physical machines. So now this term machine has become, slightly diversified. But the idea is that there is some kind of a container, there is some kind of a place where your code is running. It could even be an online platform, for example. But the idea is that there is some kind of a place where execution can take place. So we are going to show how the software elements of your system are allocated across these containing elements, or execution elements, whatever you call them. So, the first thing that we would like to do then is to show these containing elements, and these containing elements are shown as boxes. These are different from the boxes that we usually use, because these boxes are basically kind of 3D boxes. Okay, they look like cuboids instead of simple rectangles. They look like cuboids, and these cuboids can be connected to each other to show any kind of communication between them. So for example, let us say this is one server entity, and then these are two client entities. We saw how you can connect them using the TCP IP stack. So basically, whatever we did using sockets, that is also for in networking terminology, we call it the TCP IP stack. That you made the communication via using these TCP and IP. These are two protocols that you'll come to know when you study networks. So anyhow, so this is one way to show hardware. In this case, I'm showing that there are three different hardware elements. Again, the term hardware is not really too strict. It could be virtual hardware, it could be anything else, it could be like a platform or something. But the idea is that it is some place where code is being executed. So I'm saying that there is a server, and then there are two clients which are connected to the server via TCP IP. So this is one way to show these hardware components. And then when you want to show that there is a particular software element, which is and by the way, this I have already told you that online platforms are also often shown in the same fashion. So this so-called hardware, it need not necessarily be hardware, it could be a platform. And there can be nesting also. So I told you that sometimes a Docker container runs inside a virtual machine, and a virtual machine runs inside over a physical machine. So there is like a nesting. So you can, by the way, if you want to show this nesting within your diagrams as well, you can show a smaller node, a smaller box, cuboid within a larger cuboid, in order to show some kind of nesting. That is also possible. People do that. And then the major aspect of an allocation diagram is to show how software elements go and sit over these execution environments, or execution machines. So to sorry to do that, there is an option of using the deploy connection between an artifact and these so-called elements. Okay, so how do you do that? Something like this. You have an artifact here, and you want to deploy. You say that deploy on this particular hardware element. It means that this particular software module, or whatever you call it, it gets deployed over this particular execution environment. These artifacts, by the way, are essentially the way in which you package and ship your software elements. Okay, so I'm not sure whether you guys are aware of it, but basically Java has a way to zip your system's code using files called jar and var files, JAR and WAR. Then a common way to do that is also through zip. So through zip you can probably send your code as well as any executable that is required, and then you can directly send executables as well, like a .exe file. So all these are essentially software deliverables. They are called artifacts. Artifacts can also be just source code. So any piece of software element that is a part of your system, if you want to show how is it going to be sitting on a running snapshot of my system, then you can use the deploy connection. Sometimes you can also use your own custom connections, as in, you do not want to write the term deploy, you want to write something else, you want to convey some information. So then in general, UML has an option of stereotyping. So stereotyping basically means you put some text within these two symbols. Okay, they look like the insertion and what is that operator called? I forgot that name. So basically, the see out and see in related stuff, right? They look very similar to that. So you can use that to stereotype a connection or a box in UML. So you can use custom connections as well by putting your own names. So this is an example. For example, this is a ticket booking mobile application. So I prepare the war file. War file is essentially in C++ terminology. You can basically say it's a file that is containing a lot of .o files and then an executable, something like that. So you deploy it. This is a web application, by the way. So you deploy it on AWS. AWS is a platform, Amazon Web Services, and within that you have taken a virtual machine, and within that I'm also saying that there is a Tomcat server. Okay, so server here is not really a physical server. It's basically a web server. So you can see the kind of liberty people can take in displaying these elements. They are not necessarily hardware all the time. They could be software elements, they could be containers. The overall idea is to convey some information, right? So I'm trying to say that there is a Tomcat server running within an EC2 instance. This is what is being conveyed here. And similarly, I have shown Google Play Store as a platform. Okay, so the APK file, APK, if you guys know, for Android applications, this is the, I think this is the standard way to ship Android applications through APK files. So what I'm trying to show here is that there is an APK file which gets uploaded to the Play Store, and then on the mobile phone, via internet, you basically search where this application is, and once you figure out this is the application I want to install, you download that APK from Play Store at your own mobile phone. So I'm calling it migrates from here to here, and then you install the application, and after that this application connects with the server. So this is one way to give you a brief idea of what a deployment diagram looks like. As I said, you can take up your own liberty here. A lot of people draw many things in these deployment diagrams. For example, within the whole cuboid, they draw some kind of connections between the modules. So it's like a hybrid of a deployment diagram and, let us say, a class diagram. So that people do that, by the way. So it's up to you, how do you use the deployment diagram. The overall idea is to convey how parts of your system are going to be deployed on different platforms, machines, containers, whatever it is. So this is how a deployment diagram works. And if your project, by the way, has is a project which is going to run on multiple boundaries, multiple systems, then maybe it is a good idea to think about creating a deployment diagram. Okay, any questions? Yeah, the last week content is actually not too much. I could have probably covered it live in the lecture itself. Okay, so I hope there are no questions. You can of course come back to me as well. So let me stop here. I have some more code, probably the final code of the course to show you, and this is the last lecture. Share. Okay. So for the past 3 weeks, and now this is the fourth week's content, the idea was to learn some skills in the system building domain. These are skills that you are not really taught directly. You just have to pick it up as and when required. So we discussed these skills here so that you get at least accustomed to the concepts, and maybe later onwards, if a day comes when you're really when you're required to use these concepts, you at least know that it is possible to do so. So that is why we looked at multi-threading, we looked at networking, we looked at creating GUI using Qt. So there's one last piece of code that I'm just going to show you today, and that is about creating shared memories and forking processes. These are the last part of this course. So, if you remember, when we discussed threads, at that point of time, I used a term that threads are essentially lightweight processes. Okay, I said that lightweight processes because these threads actually share variables between them. They actually share some data with each other, and because of this, the threads can easily communicate with each other as well. Right? You can probably set a particular global variable's value and in one thread, and the other thread can read it. And we had a I think we had an example to where the two threads were reading just one single global variable, and with the help of that there was some kind of synchronization. We were able to make sure that thread 1 runs first and then only thread 2 starts, something like this. So it is possible to do that if you have any piece of common memory, any common memory block where one thread can write and the other thread can read, and vice versa. But what if we want these things to happen for two processes? Okay, so this is possible for threads because they share a common memory by default. But what if we have two running processes, and these two running processes want to share some data with each other? So how do we do that? Well, there are some ways to do so. There is a way to pass a message from one process to another, but I personally prefer the way of using shared memory. So shared memory is essentially a kind of block of memory that is allocated by the operating system within the main memory, which, as its name suggests, is shared among all the processes that are there currently in the memory. So just to give you a brief overview, whenever a particular process is created, we have probably talked about it in brief during the threading part, that each process has its own memory space, right? So in this memory space, the process can store its variables, the global variables, the stack frames, everything goes on in and is allocated in this memory space, which is specific to this particular process. Of course, all these processes are lying within the main memory only, but there are boundaries, right? So from, let us say, address number X to address number Y, it is allocated to process P1. From address Y plus 1 to Z, it is allocated to P2, so on and so forth. So if any of these processes make an attempt to access a memory location that is not associated with them, the operating system will not let that happen. It will block that access. This is the security model of the operating system, with the help of which one process cannot mess up another process. But when it comes to shared memory, it is basically a common block of memory within the main memory, where anyone can read or anyone can write. Okay, so the operating system basically switches off the security for this part of the memory. So now from here onwards, if you have a way to access it somehow, if you can reach that location, then you can simply access it. The operating system will not mind. And so the only thing that you are required in such a scenario is a key. So a key is basically an identifier. It represents where exactly within the main memory is this shared memory block. So if you want to access that block, you should have this particular key. And once you have the key, you can simply go and do whatever you want. So you can if you, so this process P1 can go and write some data in this particular shared memory if it has access to the memory key. And similarly, this this process P2 which wants to, so there is a communication between P1 and P2. This process P2, as long as it has the same key as this one, it can read this data, and so there is a kind of inter process communication. The problem here, of course, is that there is really no check being done on this shared memory, right? So any process that has access to this key, memory key, can go ahead and access this shared memory. Okay, so now the onus of making sure that this key is not available to other processes, that lies on the developer, on the person who's going to use it. Not only this, sometimes multiple processes might want to read or write this memory. The operating system doesn't put any constraints whatsoever. Okay, whomsoever wants to read, you can read. Whomsoever wants to write, you can write. So there could be cases where there is a kind of inconsistency. You expected the memory to have some other content, but because of an illegal read or an illegal write, the content has become corrupted or whatever it is. So these problems must be resolved at the level of the developer. So it is your responsibility to make sure that the access to this shared memory is done via a proper mechanism, that the key is not available to all, and it is only available to the processes which need it and not to any other process. So that is the onus of doing this is on you. So this is a typical flow of what happens whenever you are going to create these shared memories. What really happens is that there is a function called shm get. This shm get stands for shared memory get the shared memory, right? And what this function really needs is, number one, a key. This key has to be generated by you. So you say this is the kind of identification with which I am going to access this particular shared memory. And the other thing being the size. I want a shared memory of, let us say, 10 bytes or 20 bytes or 100 bytes. So you need to give these pieces of information to SHM get. There are some flags as the third argument, and these flags decide upon what should be the access rights, to this particular memory location. But at the first time when you are creating the shared memory, there is a special flag called IPC create, CREAT. So if you pass on that flag, operating system will know that you are asking for a new memory. Now, the major part here seems to be how to manage that key, right? Because this key, as long as this key is available to the processes, each process can participate in the overall communication, right? So the key becomes a really important factor. So how can we make sure that there are multiple communicating processes, and they all have the same required key? Well, in order to do that, there is a method that you can use. It's called the FTOK function. The FTOK function is what it does. It basically takes a string and a number, and then it uses this string and a number to generate a key for you. So then you really don't have to remember, some kind of a long integer. The only thing that you have to remember is, let us say, a pass phrase and a pass number. So as long as there are two processes which have this passphrase and this pass number, you can figure out, because this FTOK will produce the same key every time you provide you provide the same values of this pass phase and this pass string and this pass number. So with the help of this, you can in fact create the same key every time you want to. And so now the task that remains is, you need to code or provide this string as well as this number to all the processes. It can also be, for example, used like a password. So if you say that there are multiple processes, and these multiple processes can only access this shared memory if the same password is provided, for all the processes, something like this. So the idea is to make sure some kind of security mechanism is there, and in order to do that, this is what you can do. Okay, so now the other thing that you have to understand is that just creation of this memory doesn't mean you get access to it. Okay, because this is not really a memory that is owned by the creating process. Please keep this in mind. Okay, it is a general block within the main memory, which is basically free for all. So if you want to access this memory, you have to go and call another function called shm80, which basically means please attach this memory to my memory space to my so that I can access it. So what happens is any process that wants to access this shared memory requests the operating system to attach this memory or this process, no, this with the process so that this process can access it. What this shm80 returns is basically a void pointer, void asterisk. If you remember, we discussed the void asterisk in the previous previous to previous lecture. So there what we do is with the help of this void pointer, it can then be interpreted as any pointer as you want, right? So essentially it's very similar to the malloc thing, that there is a piece of memory, there is a block of memory. It is up to you how you want to interpret it. You can interpret it as a character string, you can interpret it as an object, you can interpret it as a long, whatever you want, right? You basically typecast the pointer properly, and then you can use it the way you want to. So this whatever this shm80 returns, you have to you have to typecast it to a proper value, and then you can use this memory location similar to how you use any other pointer. Okay, you can do asterisk ptr, and then this is the value, or if you want to assign something, asterisk ptr equal to whatever value you want to. After the job is done, you use the shmdt, that is the opposite of shm80. You basically say detach this shared memory from this process. And once all of these things are done, you finally make a call to shmctl, which is basically a way to tell the operating system that I no longer need this shared memory. And it basically marks it for deletion. Please keep in mind that the memory doesn't get deleted straight away. Why? Because it may be being accessed by multiple processes at the same time. So in this, so this is why we need to figure out a way to do this. So what happens is the shared memory is marked for deletion. And what the operating system does is that it keeps on checking how many processes are currently attached to this shared memory, and as soon as all the processes which were attached to it have completed or they have detached themselves, at that point of time it is up to the operating system to figure out a suitable time to delete the shared memory. So then the block gets deleted. We will have a look at it in the code as well. But there's one last piece of programming knowledge that we need to know, and after that we can basically end this course. And this is the idea of forking. So we saw how you can create a new thread of execution using the POSIX API, right? So the major difference, by the way, between, and then you see that it is also possible to communicate between two processes, by the way. But the major difference between a thread and a process is that a thread is can threads can share their threads can share their uh, what can I say? They can share some kind of memory segment, right? And with the help of this, there are variables out there who can which can be shared between each other, right? So there is a data part which is shared by the threads. Is there a question? Okay, so there is a data segment which is shared by these threads. Now, in many cases, this is desirable because you can easily communicate between the threads. But in certain cases, this could be a problem also. Why? Because from the security perspective, you do not want different threads to be able to access each other's data or some kind of global data. So in such a scenario, it is certainly advisable that you create a copy of the variables that are there in in your program right now, and then let them be independent of each other. They cannot interfere with each other. So what you really need to do is, instead of creating a thread, you need to create a new process. And if you want to do something like this, there is a system call for it called the fork system call. And if you I think you guys at least know what a system call is. If not know, at least you remember this term. We have discussed what a system call is during ITP. So system calls are basically the ways in which you interact with the kernel of your operating system. So anyhow, so there is a system called for forking, and it's called fork. And in C++, you also have a function with the same name called fork. With the help of this function, what you can do is you can create a new process. Please keep this in mind. This is not a new thread. This is a new process that is being created. And this process is basically a replica of its parent. So parent as in the process which called fork, that becomes the parent, and the new process is the child process. And this child is essentially a copy of its parent. So the code segment, all the data variables that are part of the parent process, they are all replicated. They are all, a copy is created. There is only one difference between the parent and the child, and that is the call to the fork system call. Okay, this fork system call returns a value, and this value is different in the parent and it is different in the child. So just to give you an idea, let us say I am running a process here, and I do something like this: PID equal to fork. So at this point of time, a new process will be created, and it will be an exact replica of this current process. And an exact replica, as in even the program counter is going to be the same as for this particular process, right? So if I just executed this statement, the program counter will probably be pointing somewhere here, right? The next statement. So in the newly created process also, the execution will start from the immediately next statement that is there after fork. Immediately next, as in not in terms of C++, but in terms of assembly language. Whatever is the next statement that is supposed to be executed in assembly language, that will also be executed. Now that statement will be executed twice in two different processes. And now you might feel, how is this useful, right? I'm just going to do the same computation twice. Well, this is why the PID is important. So you can actually write an if condition here, and with the help of this if condition, you can do a bifurcation. Why? Because, so for example, if the PID is less than 0, then the fork failed. That it usually doesn't happen, but it is a good idea to check. But if this PID is 0, then it means that this PID value will be 0 only in the child process, the newly created process. Whereas in the parent process, this PID will be some positive value, and this positive value is basically the process ID of the newly created process. So if you write this is how you basically do a bifurcation whenever you are doing fork. What this code, okay, this part of the code will only be executed in the newly created process, and this part of the code will only be executed in the parent process. So at this point, you can do a bifurcation. You can put it in a block, and then whatever code is executed, that will be executed only in child, and whatever code is executed here, that will be executed only in the parent. So this way, this with the help of this returned value of fork, you can actually do a bifurcation. You can distribute your code into two different parts. One part will be executed when there is a forking, when one part is executed in the parent, the other part is executed in the child. And by the way, you have to be a bit careful about using fork, because let us say if you use two forks, okay, then and you have to figure out that you have to know that from this point onwards, the code will be executed twice, right? So if you do not use these if else conditions properly, it is possible to come up with a whole a whole bunch of new processes, because one process will give birth to two. Basically, now there is parent and there is a child, and then if another fork is written right after this, that will basically spawn four processes, because both these processes will now fork one more. So now you total have four processes in general. So you have to be a bit careful that beyond the fork statement, everything will be executed twice the number of times than what it was before. So now let us have a look at some code. Do you have any questions, by the way? The chats. Okay, so I can also see what I can also, you can also of course come back and see this later, and then you can drop me your questions later. So let me stop this. Is my VM open? Yes, it is. Okay. Can you guys see my virtual machine? I think you can. Right. Okay. So let me first start with the fork itself. So this is an example of forking. I think it is already open. Is it? Yes, it is open. So this is an example of fork. Okay. So you can see that I have put some if else conditions here, right? Why do I do this? Because the returned value of fork will be different in the parent as well as child process. I should have also checked for the less than zero case, I know, but yeah, for now just assume that the forks are going to succeed. So in this case, what am I doing is, this is the first fork. This will change one process into two processes. Okay, and then the next thing that will happen is, within these if as well as within these else, I am putting some more forks. Okay, so there are basically three different levels of forks you can see here, right? This is the first level fork. This is this, I mean, this and this are the second level forks. So basically there is one process, then there will be two forks that will be executed, and then there will be there's one more level of fork here. So what it is actually going to do is, it is going to create a hierarchy of processes. And if you run this code, make all, this is a very simple piece of code. The family tree, let me just put it here, and let me just show you what is tree.txt. So each process has a process ID. Okay, this ID is assigned by the operating system. So this is the level one, the first process. Okay, and it has a process ID of 10402. So then the next level of forks will give you second level processes. These second level processes are 10404 and 10403. Usually you will find these process IDs in either they are sequence, they are in a sequence, or there might be a few integers apart usually. Okay, it is not necessary, you cannot guarantee this, but usually it looks like this. So these are two, so this is my original process. It has the PID 10402. Then I have two immediate children. One has 10403 ID and the other one has 10404. And then these two child processes also spawn two child processes each. So that is what I was saying, that when you use fork, you have to be a little careful, because this can become exponential very easily. So then these two L2 processes give rise to four level 3 processes. Okay, and these are here: 405, 406, 407, and 408. So and now if you start doing forking in these level 3 processes as well, it will give rise to even more processes. So whenever you use fork, you have to be a little careful, because the number of processes, if the code is not written properly, can explode very easily. So please keep this in mind. So any questions on forking? Any doubts? So you are basically creating a tree. There is a parent, and then there becomes a child. There comes a child. Then the child itself can become a parent and fork another child. And of course the parent can have multiple children as well. If you put multiple fox, then that can be done as well. Any questions? Okay, so that is it for the forking part. Now let us have a look at the shared memory as well. So I have two programs here for shared memory. So this is the first program. The idea is that there is one process which is going to create the shared memory and then put some data in it. Okay, and then this process basically exits, and then another process comes into the picture. It has to know the same key, the key which was used to create the shared memory. The process needs to know the second process needs to know the same key. As long as it has access to that key, it can go and read whatever was written by this process. So here I'm using two inputs. One I'm calling as passcode, the other one is pass number. So this is basically the reason this is a good way to do it is because now you don't really have to remember a long number. Okay, you are basically going to remember pass phrases and numbers, right? And then your key can be derived out of it by calling ftok. So the it is guaranteed that if these two arguments are same, the output will also be the same. This is guaranteed, right? So every time I call ftok with these two inputs, whatever is the key, whatever, I don't really need to know, I don't really need to remember. The key will be exactly the same whenever the inputs are exactly the same. So then with the help of this, I will generate some key. You can actually go and print it and check also, but there is some, it is some large number. And then what you do is you basically call the shm get function. Here you pass the key and the size of the shared memory that you want. And here you are going to provide this flag called IPC underscore create. And this will basically tell the operating system that I am asking for a new shared memory to be created. And if this value, so this call returns an id for the newly created shared memory. And if you do not have if enough memory in the main memory right now, or because of some errors, if it fails, then this value will be a negative value. Otherwise, if it's a positive value, it means that the shared memory got created. So the next step is to attach the process to this shared memory, and this is done using the shm at function. It needs the ID of the shared memory. There are some other things that for now you don't really need to know. So then what is this? The idea is to provide a pointer to this particular shared memory. As soon as you attach yourself, you are given a pointer to access this memory. By default, it will be void asterisk. If you want to use this memory location in some other fashion, for example, to store a long or even an object, you simply typecast it properly, and then you use this pointer for your own for the way you want to use it. So here you do this is similar to using a typical pointer in C and C++. You simply do value at this memory pointer equals the data that I want to store, and that is it. After I am done, I simply detach this process from this memory. Now the let me in fact let me run this. So it has created the shared memory. Any questions? So it has created the shared memory and stored this data item there. Now there is another program. Beginning is pretty much the same, right? You again provide the same passcode and pass number, you generate the key. So this key will be exactly the same key as the one that was generated in the previous case. And then you do the shm get. Here you are not going to give the IPC create now, because you know that the memory is already created. You'll get the ID. Here again the same thing, you attach yourself with that shared memory. And once you get this pointer, now you can read the data back using a simple pointer usage, right? So long data equal to value at this pointer, and then you can print it. Finally you detach yourself, and this is how you once the memory has filled up it has fulfilled its purpose, you can request it to be deleted. So this is the deletion part. You give IPC underscore RMID and you are done. So this is, and again this marks the memory for deletion. It will be deleted only after it will be deleted at some later point of time when operating system feels like, but you have basically marked it for deletion. So now, by the way, I have written the value 42 there. So if I run it, this 42 is basically read from that same shared memory which was created by the other process, and then it would have been marked for deletion. So there is a good chance that by now that memory no longer exists. Okay, this is it. Any queries? So then, if there are no queries, this is basically it for object-oriented methodology. The content for the last 3 weeks is also available on Google Drive and YouTube. So please go through it. If you have any questions, doubts, you can certainly send me an email and ask. But from our side, this was basically the last lecture. Okay. So again, any questions? Okay, guys. Then thank you. Bye.